You can calculate process capability indices for non-normal data using one of two methods. You can either use the percentile method or the Z-score method. If you are making decisions based on capability indices and you don't know the difference between these two methods, then this video is for you. I'm going to introduce to you the percentile method of calculation, and I'll explain how it's a logical generalization of the definition of process capability indices. It's the default method in JMP, and it's also an international standard. Then I'm going to explain to you why the Z-score method is potentially a superior method of calculation, particularly when you're driving engineering decisions based on the values of your capability indices. Okay, so let me jump straight in, and I'm going to start off by just showing you some data. So here I have a set of data which are best represented as a log normal distribution. And now let me do process capability on these data. This is the formula for CPK for the case of a single-sided specification limit. And if I plug numbers into this, then you see the value evaluates to a number very different to the number reported by JMP. So what's going on? Well, CPK kind of gives you an indication of where the process is located relative to the specification limit. But this measure of location for a normal distribution, you can take the mean value as a measure of location. But for a skewed distribution, the median is a more appropriate measure of location. So maybe I just need to modify this equation to have the median instead of the mean. If I plug this number in, then I get a number even larger. So that didn't work out, but my motivation was correct. When I'm thinking about median, I'm thinking about a percentage point. And JMP is actually using a technique known as the Percentiles Method. But we have to go one step further. We have to think about what's on the denominator. I've got a value 3 sigma here, which is half of 6 sigma, and 6 sigma is the width of a normal distribution. Now that value of 6 sigma is only a convention. I'm pretty sure in the 80s I used to use a figure of 5.15 sigma as the width, and that's because that represents 99% of the variation, and that's an easy number to work with. 6 sigma is more awkward, it's 99.73% of the variation. And in particular, because it's a symmetric distribution, we end up with 0.135% to the left and 1.35% to the right. And that's the clue for how I really generalize the formula for CPK. This 3 sigma is the interval from the median to the distance such that 0.135% is above that distance. I am going to refer to that as W, the effective width. And if I were to calculate that width for these data, it's 5.8 sigma. So much larger than the 3 sigma we've been using earlier. But let me just confirm that calculation by coming back to JMP. So for these data, the specification is 190, the median is 80, and we have a standard deviation of 39. So I plug the numbers in, I get a value of 0.486. Now that looks like a typographical error that we want 0.468. What's going on here? Well, I've used the value of 80, and 80 is the median of the data. If I were to use the median of the actual theoretical distribution of that log normal distribution, then the median for that is 84. So I'm going to plug that in. If you have to take that on trust. If you would like me to give an explanation on that, I can do that in a future video. Now, when I plug these numbers in, we do get the correct answer. The correct answer in that it's agreeing with the number reported by JMP of 0.468. So far so good. We can now understand how this capability index, which was initially defined for a normal distribution, is generalized to other types of distributions based on this percentile method of calculation. But there's a problem, and the problem comes in how we use our capability indices. I think it's fair to say that normally when we use them, we have target values in mind. And therefore we are comparing the number we calculate against this target value. Now, If we're going to make decisions based on that target value, we need to make sure we have consistent performance in relation to that number. That's to say that if I take a capability index and convert it into a measure of process performance, let's say non-conformance, we should have a consistent relationship. And that, unfortunately, is not the case. To illustrate that, let me look at these data. SPCX is normally distributed, and it gives me a CPK of 0.385. Now let's look at SPCY. It also gives me a capability index of 0.385. However, if you look at the non-conformance rates, they're very different. So does a CPK of 0.385 give you non-conformance larger than 12% or less than 5%? It depends on what type of distribution you have. Now that doesn't make sense, or it doesn't make sense if you're going to have a threshold for your capability index and drive engineering decisions based on that target value. Let me give you another illustration of this. For these data, SPCX has a non-conformance rate of about 4.9%, and SPCY has got the same non-conformance rate, 4.89. So both of these have the same level of process performance, but the normal distribution has a CPK of 0.55, whereas the log normal distribution only has a CPK of 0.385. So the same performance for the process results in different capability indices, and that just doesn't feel right, and it doesn't make sense if you're driving engineering decisions again. So what's the solution to this? Well, the solution is we have to abandon the percentile method of calculation and implement an alternative method. That alternative method is known as the Z-score method. Now, I'm not going to go into the mathematics of it, but I will illustrate it by example. In fact, I can take these same data that I've been working with, but now I'm going to take this log normal distribution and I'm going to remove the process capability and I'm going to perform it again. So I want to do the analysis based on a non-normal distribution and it's log normal, but I have an additional option, and that option is to use the Z-score method. So now my capability index is 0.552, which is in agreement with what I have for the normal distribution. So I now have consistent decision making, that the capability indices I compute have the same conversion. If I take a particular number like 0.552, the non-conformance rate is the same irrespective of whether I have a non-normal distribution or a normal distribution. The key takeaway is this: if I use the Z-score method, then when I calculate a capability index, the associated non-conformance rate is the same irrespective of if I have a normal distribution or a non-normal distribution. So that means you're going to make more consistent engineering decisions. I hope you found this video helpful. If you did, then please give it a like and think about subscribing so you can easily find future videos. All the best. Bye for now.